Hello, this is Jack Jackson. In this video, we're going to talk about p-series. So one of the most important class of functions is a set of power functions. F of x equals x to the p for some constant power p. When we restrict the domain of a power function to the set of natural numbers and then sum, we have a p-series. So the sum k equals 1 to infinity of k to the p power for some constant p is a p-series. We could use the integral test to determine exactly which values of p make the p-series converge and which values of p make it diverge. First, notice that the only hope a p-series has of converging is if p is a negative number, because the limit as k goes to infinity of k to the p is infinity when p is positive. It's 1 if p equals 0, and it's 0 if p is a negative number. So the divergence test tells us that the series diverges if p is a positive number or 0. So from here on, we're going to assume p is negative. Let f of x equals x to the p. F is positive valued for positive x. F is continuous for positive x. Remember, power functions, the only place we might have a discontinuity was when x is 0. F prime of x is the power rule, says is p times x to the p minus 1. And notice that that's going to be negative. When x is positive, x to any power, positive or negative, it'll be negative, is positive number. But then the p out front is negative. So this derivative is negative when p is negative and x is positive. So f is decreasing for positive values of x. Now let's look at the integral. We have two cases to consider for the antiderivative. If p is not negative 1, then the normal power rule applies. So let's look at the case where p is not negative 1. That's most of the time. So the integral from 1 to infinity of f of x dx is the integral from 1 to infinity of x to the p dx. First of all, that's the integrate from 1 to b, and then take the limit as b goes to infinity. That's what's meant by the improper integral here. Do the power rule, add 1 to the power and divide by the new power. So the antiderivative is 1 over p plus 1 times x to the p plus 1. And again, that works anytime p is not negative 1. We're going to evaluate from 1 to b, so that's b to the power p plus 1 minus 1 to the power p plus 1. 1 to the power p plus 1 is 1. So we have b to the p plus 1 minus 1. The 1 over p plus 1 I brought out front of the limit sign. Now take the limit as b goes to infinity. Well, we've got two cases. If p is greater than negative 1, then the power p plus 1 is positive, and this thing goes to infinity. But if p is less than negative 1, p plus 1 is negative, and so this part goes to 0. When it goes to 0, the whole thing converges to negative 1 times that 1 over p plus 1. But if p is greater than 1, that goes to infinity. So the integral test says the series p-series is going to diverge to infinity if p is greater than negative 1, and if p is less than negative 1, it converges to some positive number s, and the s really has to be between 0 and the opposite of p plus 1. First of all, just the fact that it's positive term sequences tells you that you're going to get a number bigger than 0. In fact, I think we can, if we're just this, the first term is 1. So in fact, we could say actually it's between 1 and the opposite of p plus 1. Remember, p plus 1 is negative, and 1 over that's negative. The minus out front makes it positive, so it will be a positive sum. Now, let's see what happens when p equals negative 1. Remember that for this value, we have a different antiderivative since the normal power rule doesn't apply. So when the power is negative 1, the integral of x to the p is the integral of x to the negative 1. Again, I put the b here, take the limit as always. The antiderivative this time, the antiderivative is natural logarithm of the absolute value of x. So whether you think of it as x to the negative 1 power or 1 over x, the antiderivative is a logarithm of the absolute value of x. Now I could drop the absolute value of x because everything's positive here. So it's log of x, evaluate it at b and 1, subtract there, log of 1 is 0, so this is just the logarithm of b. And as b goes to infinity, the log of b also goes to infinity. So that one diverges as well. So the conclusion is a p-series the sum equals k from k equals 1 to infinity of k to the p power for some constant p. Okay. Converges if and only if p is less than -1. So the smaller the power, sort of the faster it converges, but it does the lower the sum's going to be. Now, some books, in fact, most books will write this as a different way. They'll write the p-series as the sum of k to the negative p, making p positive and putting the negative out there. With that notation, then the rule is backwards. It's the series converges when p is greater than 1. Now, I prefer to say it the way I do because, first of all, when you do k to the p power, p actually is the power. So the p series is a power series with p being the power. Just makes more sense. Plus, bigger power means a bigger sum for S sub n. So if the power is too big, the series diverges. How much is too big? Well, anything bigger than -1. So I'll prefer to write it that way. But either way, that's the same result. Okay, we're going to look at specifically when p is -1 a little bit in the next video. It's got a special name. It's called the harmonic series. And so we'll talk about that a little bit more in our next video.